Okay, so we talked a lot about order relations. So we were given examples of order relations. We were talking about minimal elements, maximal elements. Why would we even need to talk about them? What are they useful for? Well, again, you'll see a lot of graphs, in particular a lot of graphs of order relations called DAGs later on in your computer science career, and you will model a lot of things as those order relations. But now let's look at kind of an unexpected place where they come up. And they come up in, let's go back to logic, proofs. Surprisingly, there is a principle that's very, very useful for proving things about natural numbers and their subsets, and it really relies on the notion of the order. So here it is. It's called the well-ordering principle. And what it says that any non-empty subset of natural numbers contains the least elements. Let's be generous here and include 0 into natural numbers. It will be useful. Actually, we can even extend well-ordering principle later on, saying that if you throw any finite amount of stuff into natural numbers, then this principle still holds. Or alternatively, you could say I'm starting with 0, but maybe let me rename my 0 to 1, my 1 to 2, and so on, and say that the well principle holds. And and more important thing is that the order that we are talking about here is our usual x less than or equal to y. So what do we mean when we talk about subsets of natural numbers, non-empty subset of natural numbers? Well, there are lots of them, and different proofs are going to give us different ones. But if you want an example, you could think about even numbers. Is it a subset of natural numbers? Sure, or actually better, let's say all numbers that are divisible by 2. Is there a smallest such number? Yeah, 2 is the smallest number that's divisible by 2. By well-ordering principle, we do have it. By well-ordering principle, we do have the smallest prime number. We have the smallest square number. And what we are going to use in proofs, every time we will be trying to prove that something is true for all natural numbers. We would be able to assume, to start by contradiction by saying, let's take all the places where it's not true. Well, then there is a minimal point, smallest natural number for which it's not true. Now we got something that we could talk about. It's a number. Is it even? Is it odd? Is it a square? We could look at all of those cases and come up with an answer. So, as an example, let's look at that puzzle about coins. So the question was, what is the largest amount that cannot be paid by using only existing coins? So let's try it. We definitely cannot pay 1. We cannot pay 2. We can't pay 3, but can we pay 4? No. 5 is still a problem. 6 is fine. 7, not really. If we have 2 of the 3s, it's too little. 3 of the 3s is too much. 3 and 5 is too much. 5 and just 5 is too little. 2 5s is too much. Okay. What about 8? 3 and 5. That sounds good. What about 9? 3 3 3. 10. 5 and 5. 11. 5 3 and 3. Okay, becoming a pattern. So what it looks like is that any number that's greater than 7, 8 and above, maybe it can be paid with only coins 3, 5, 10, and 25. And actually, in fact, we only need 3 and 5 because 10 and 25 we can just make out of 5s. Let's prove it. Let's prove that every amount of change that's 8 or more than 8 can be paid with only 3-cent and 5-cent coins. So here is a well-ordering principle that we are going to use. Any non-empty subset of natural numbers contains the least element with respect to less than or equal relation. And here's what we are trying to prove. Every natural number x that's greater than 7 can be written as a sum of the 3's and sum of the 5's. So this is a more formal way of saying any amount greater than 7 can be paid with 3-cent and 5-cent coin. So let's do the proof. So we want to prove that every amount can be paid. But let's do it by contradiction. Let's suppose that there is something greater than 7 which cannot be paid, but 3 is 5. Maybe there is one such thing, maybe there is more than one such thing. Let's just take a set of all the numbers greater than 7 which cannot be paid with 3's and 5's. All the numbers x such that there is no such y and z that x is equal 3y plus 5z. And here is where the well-ordering principle comes in. Because we could say, let's take the set of all such amounts, and since we assume that there is something in that set, by well-ordering principle, there is a least element of that set. Let's call it n. So again, what will be that n? It's the smallest number that's greater than 7 and that cannot be paid with 3's and 5's. It's the smallest number. This is what we are going to use. This is going to be what makes our proof work. Because if we look at n minus 3, it cannot be paid with 3's and 5's. But wait a moment, we say that n is the smallest such number greater than 7. Okay, so n minus 3 must be less than 7. So here is our setup. N is greater than 7 and it cannot be paid with 3's and 5's. N minus 3 is less than or equal to 7 and should not be payable with 3's and 5's. If n is payable with 3's and 5's, we just add n minus 3 is payable with 3's and 5's, we just add on an extra 3 cents and we get n, and we assume that we cannot do it. So all that's left to do for us is to show that we cannot really get the numbers that such that n minus 3 is less than or equal to 7, but n is greater than 7 such that it's not payable with 3's and 5's. So let's do it. We have 3 cases because it could be that our n is 8, it could be that our n is 9, or it could be that our n is 10. If n is any less, it won't be greater than 7. If n is any greater than n minus 3, will not be less than 7. So those 3 are our only possibilities. Let's look at all of them. What if our n were equal to 10, so n minus 3 is 7? Can we pay n with 2's and 5's? Yes, because 10 is payable with 2 5's. No problem. What if our n minus 3 is 6? Then n is 9. 3 of the 3's, not an issue. N minus 3 is 5. N is 8. We could do 8. 3 plus 5. So now we are out of cases because we cannot take anything smaller, we cannot take anything larger, and we cannot take anything that's not an integer. In all of the 3 cases, we got a contradiction because we managed to pay 10, 9, and 8, the only possible numbers, with only 3's and 5's. What does it tell us? The only way this can happen is if the set S, of which n is the smallest number by well-ordering principle, if that set were empty. What does it mean for that set to be empty? That means that there are no numbers that are greater than 7 that are not representable as sum of the 3s and 5s. But that's exactly what we wanted to prove. So here's how we got our answer. The set of those things must have been empty. Otherwise, by well-ordering principle, we get something that leads us to a contradiction. And therefore, every x that's greater than 7 can be written as sum of some number of 3s and some number of 5s.